Hey folks, let's talk about ramps. So this is a box. It has many box-like qualities. Box's name is Box. Box is sitting on a ramp. Good box. Box wants you to draw a free body diagram of it as it sits motionless on the ramp. Will you do this for Box? Ha! I sure will. Pause the video now and try it at home. Oh good, you're back. Now I'm going to draw my free body diagram, and we will compare mine with yours, because I know all of you definitely jumped at the opportunity to help Box. Who wouldn't? Look how adorable he is. All right, so first off, I'm assuming this is on Earth, like most of our examples are. So Earth is pulling down on Box with the force of gravity. Now, sometimes you'll see this force labeled different ways. It could be labeled Fg for force of gravity, it could be labeled W for weight, or it could just be labeled mg. That's the equation to find the force of gravity. It's the object's mass times 9.81. However it's labeled, you've got the force of gravity, and it always points straight down toward the center of Earth. Now, since Box is sitting on the ramp, he's sitting on a surface, there's going to be a normal force. From Newton's third law, if you exert a force on a surface, the surface exerts a force back on you. Now that force, unlike what we've done in previous examples, is not going to be straight up, because now the surface he's on is not perfectly horizontal. The normal force always points perpendicular to the surface. In fact, the word normal just means perpendicular. So when I say normal force, I'm just saying perpendicular force. Sometimes you'll see that labeled F with a little subscript N, sometimes you'll see it just labeled N. I don't like labeling it only N because then it's easy to confuse with the unit newtons, but some people do it anyway. And if that were it, then poor Box would just be sliding down the ramp. But it says specifically in the problem setup that Box is sitting motionless. So there's got to be another force preventing him from sliding down the ramp, and you guessed it, it's good old friction. Now, friction is parallel to the surface. So it's not going to be a horizontal force as it's been in the past, it's going to be up and to the right. And specifically, in this case, it's going to be static friction, but if Box were sliding, there would be kinetic friction there instead. I'm just going to leave it labeled FF for force of friction. And those are all the forces acting on him. Cool. Now let's slap some values on here. Let's assume the ramp is at an angle of 30 degrees above the horizontal and Box has a mass of 20 kilograms. What are the values for the normal force and the friction force? And then what must be the minimum coefficient of static friction? So this is the part that can get a little bit nasty if you don't have, this little trick up your sleeve. When you're first solving force-related problems, as I've mentioned before, you're going to want to break each force individually into x and y components. But that's going to take a little bit of time because the normal force is pointing up and to the left, friction is pointing up and to the right, so I would have to somehow figure out where each angle fits, what angle is what, and break it all down that way. And it's doable, but it's not a whole lot of fun. But there's another option here, so you don't have to break down normal force and friction into components. Because normal force is always perpendicular to a surface, and friction is always parallel to a surface, I also know that my y-axis is always perpendicular to my x-axis, and friction is always perpendicular to normal force. So rather than setting up my coordinate frame like this, where I have y completely vertical and x completely horizontal, that's what I'm used to doing. But if instead I try something else, I'm going to put my y-axis so it perfectly aligns with my normal force. And I'm going to put my x-axis so it perfectly aligns with my friction force. That means my normal force will only have a y component and no x component. My friction force will only have an x component and no y component. I'm not completely out of the woods because, check it out, that means now my gravity force has an x and a y component. Sometimes you'll hear other people describe this as a perpendicular component and a parallel component to the ramp. If you're like me, this is a little uncomfortable because you're so used to y being perfectly vertical and x being horizontal. So what we can do is just sort of shift our view of the whole situation. Like, if I wanted y to be vertical again, I would need to grab the y-axis and move it 30 degrees this way. If I wanted the x-axis to be perfectly horizontal, I'd have to grab it and move it 30 degrees this way. And I know that because the angle of the ramp is 30 degrees right here. If I wanted to flatten the ramp, I'd have to twist it clockwise 30 degrees. I went ahead and redrew the free body diagram as simply as possible. I got rid of the ramp, got rid of the picture of the box, so it's just a point with mg pointing down, normal force up and to the left, friction up and to the right, and my axes placed on it. Now imagine grabbing the axes and tilting it, like I said, 30 degrees clockwise. And there we are. So I didn't move any of the forces relative to the x and y axes, and now it's a view that I'm comfortable with. Force of friction is just in the x, normal force is just in the y. Now I need to find an angle for my gravitational force mg. Well, before I twisted this whole thing, mg was pointing straight down, then I grabbed and twisted everything clockwise, an angle of 30 degrees. So it is an angle of 30 degrees clockwise from where it originally was. This is also a little different than a lot of the examples we've done in class, because in many of those examples, I give you an angle relative to the horizontal. This 30-degree angle is relative to the vertical. So now I'm going to break mg into x and y components. So to find what my actual component values are, let's see, I'm going to do a little bit of trig. Well, since the 30-degree angle is up here next to the vertical, my y component is actually adjacent to it. Because it's adjacent, I'm going to use cosine. Cosine is adjacent over hypotenuse. Solving for the y component only, I get mgy equals mg cosine theta. I'm going to do the exact same thing in the x direction. This time, since x is opposite my angle, it's going to get the sine. Alright, so now that I've broken each and every force into its x and y components, I'm ready to answer the question. It wanted to know the normal force and the friction force. Normal force is only in the y. Let's start with that. Well, from Newton's second law, I can say that the sum of all the forces in the y direction is equal to the box's mass times acceleration in the y direction. But since the setup to the problem says the box is sitting motionless, that means, well, it's not moving and it's not accelerating. It's got a velocity of 0 and that velocity stays constant. So that tells me right here, my y acceleration is 0. So the sum of all my forces in the y direction, which, looking at my diagram, the only forces I've got in the y direction are normal up. And then I have a downward mg cosine theta. So just for reference, I'm going to go ahead and call up positive, down negative. I'll call to the right positive x and to the left negative x. Okay? So since my normal force is pointing in the positive direction, I'll include it as positive in my list. Since my y component of gravity is pointing in the negative y direction, I'll include it as negative. And altogether, that'll equal 0. So my normal force will equal mg cosine theta. And now I can plug in my values. And I get a normal force of about 169.9 newtons. Well, now I'm going to do the exact same thing in the x direction. Once again, since box is not accelerating at all, the acceleration in the x direction is 0. And looking at my diagram, the only things I have in the x direction are friction to the right and the x component of gravity to the left. Solving for the force of friction, it's just the same as mg sine theta. All right. Now, since this is static friction, it could be, a range of values. This is the value it needs to not slide at this angle. So what is the minimum value of the coefficient of static friction? Well, I know that the force of static friction is somewhere between 0 and the coefficient of static friction times the normal force. That means my coefficient of static friction has to be greater than or equal to the force of static friction divided by the normal force. And so for this to work, the coefficient of friction needs to be at least 0.58. Thanks. Box loves you. Aw, I love you too, Box.